Okay, good morning guys. Welcome to Physics of English and welcome to the class. Today we'll be continuing our discussion on vector analysis. This is the third part 3. If you want to get all the lectures in a single course, you can download or install the Physics Hub application from the Play Store, and you can also visit the website. All the links are given in the description. Today in this video we are going to discuss about these three things: line integrals, surface integral, and volume integral. Just hold on a moment. Okay, just let me know if everything is all right, then we can start. This is an important class because a lot of questions can be expected from this one topic of line integral. And you have seen in previous year questions also, a lot of easy questions came from this line integral. So without any further ado, let's start with this line integral. So what do you basically do in evaluating the line integrals? Line integrals basically evaluating the integration of some vector function along some particular line or curve. So if in rough words we can say that. So here what we have some line or curve. For the generalized purpose, we are taking a curve, let's say a curve like this, AB, okay, and we want to find out the line integral on this curve. So the line integral is defined for a vector function. So let's take a vector function as well. So we are denoting the vector function by f. On this curve, at each and every point, the vector will be defined, right? And how we are defining the line integral, that is the question. Now to get a reference point, we are considering that our origin is situated here. So with respect to this origin, we are measuring everything, and let's consider that the x-axis is along this direction. So we are setting up the coordinate system. Now we are taking an arbitrary point. As I told you, at each and every point we can define this vector function. So we are considering that for the time being we have a point here. Let's call that point to be P. Now to assign the exact position of this point P, we have to define it with respect to the origin O. So let's say the position vector of this point P is R. Okay, so how do you define that? If I draw a line like this, then the position vector we are calling to be R. Now what is the line integral? Line integral will define as the component of f along the tangent to this line. So if this point is P, and if you want to draw a tangent at this point, then how will you, what kind of form will it give? So a tangent will look like this. A tangent will kind of look like this. I'm just drawing it bigger so that you understand. So that is T, let's say. What is T? T is the tangent. So first of all, let us write what we have defined. Firstly, we have defined that this f, obviously we are taking it a three-dimensional case, f xyz be a vector function and let f of xyz be a vector function and AB V a curve. These two things we have defined. Now how to define the line integral? As I told you, line integral of a vector function, this is the basic definition, okay? This is the line integral of a vector function f along the curve. It must be defined on some curve. For the general purpose, we have taken a curve. It may be a straight line also. Line integral of a vector function f along the curve AB is defined as the integral of the component of f at this particular point. F is acting, now its component will be there along this tangent. So the integral of the component of f along the tangent to the curve, tangent to the curve AB. Now if I consider all other points, if you consider this point, the tangent will be different. If you consider this point, the tangent will be like this. For this, tangent will be like this. If you consider this point, tangent will be like this. For this, tangent will be like this. So when you integrate all of these components, then you get the line integral. So first of all, let's calculate the component of f along a tangent PT at P. So we are defining it for a single point, then we can consider for the whole curve. And one thing I would like to tell you, this is I have already explained many times. If you have a vector, let's say like this, and you want to calculate the component along some particular direction, we have a vector, let's say A. If you want to calculate the component along a particular direction n cap, then what do? You take the dot product of A and the unit vector along that particular direction. Okay, if vector B is there, so if vector B is there, you have to take the dot product of A with B cap. Okay, so this is the general thing. So to calculate the component of f along the tangent at PT, what you have to take? You have to take the dot product of f and unit vector along PT, right? Unit vector along PT. So what is the dot product of f and unit vector along PT? F dot, what is the unit vector along PT? That is given by dr by ds. What is this dr by ds? Dr by ds is the unit vector along the tangent PT. We can write, what does this dr by ds represent? Dr by ds is a unit vector along PT, right? Then we can write the line integral. We can define it as the sum of all the points f dot dr by ds, right? Now this sum is very much close to each other. If you consider there may be millions and trillions of points in between point A and B. So what we can do? We can just convert it into integral also. So line integral is basically sum of these things from the point A to B. From A to B along the curve. So obviously if you consider different paths, let's say if you do not visit the point B along this path, if you choose another path like this or another path, then obviously the line integral will change. We'll consider some conservative, if the vector is conservative, okay, then the line integral will be independent of the path. But for the time being, in general cases, we can say that if you choose different paths, then the line integral should be different, okay, because obviously the tangent at each and every point will be different and all those things. And we define this line integral in terms of the integration. So if you are given any curve, then the curve is represented by C. So integration over some given curve C, f dot dr by ds. So this sum, instead of this using this sum, we can write it in terms of integration in this way, okay. So that is why the ultimate formula for the line integral is written as f dot dr. So this one you have to remember. This is the theory part, but for you, if you only need to remember this part, the line integral is f dot dr. Okay. Now dr, we can write it in different dimension. If you are given a one-dimensional case, let's say, then what will you write? And if you are given two-dimensional case, what will you write? I am writing it here. Let's say dr, depending on the given dimension, let's say in one dimension it will be dx I cap. If you are given in two dimension, so dx I cap plus dy j cap. If you are given a three-dimensional case, so dx I cap dy j cap dz q cap. In this way we can write, okay. Now let me give you an example of this line integral, magnetized bead on a slinky. So this is a good example of giving you the idea of line integral. For this line integral, if you closely look at, if you consider this function to be the function of force, then this line integral will give you the work done. And look at this magnetized bead on a slinky. A slinky is a pre-compressed helical spring toy. So you can see this is the slinky and a magnetic field has been applied here. So this particle will experience some force and it is traveling along this path, along this arc-like curve. Now at t equals to 0, it starts its journey from here, and because of the influence of this field, it is taking up this path like this, okay. Now at any instant here, the component of different forces are shown here. So at all the time, the force is directed along this direction. If you consider this point also, force will be directed in this along this direction. If the bead is here, then also the force will be acting along this direction. The force direction is same. You can see the lines of force. And at this point, we have drawn the tangent, because for evaluating the line integral, we have to draw the tangent at that particular point. So tangent is drawn here. So the component of the force in the direction of movement is simply the dot product of the force at the point C of t. Here let's say C of t, so function of time, right? Because if you see t goes to 0 here, if you change the time, the bead will be some other position. So the dot product of the force at that point with the tangent vector t of t, if you multiply this component f and t dot product, if you take the dot product, we get the work. F dot t as a scalar valued function that gives work per unit length along the slinky, and that is why when you integrate over the length of the slinky, we get the total work done. And F dot t alone is nothing but the work done per unit length along the slinky. C is the path of the slinky. This integral adds up to the product of f of t, f dot t and distance ds along the slinky, which is the work done. So this is a very good demonstration of the line integral. So I hope you understood the line integral pretty well. Let me just give you few things which you should remember. So you can write them as note. The first one being, as I have already told you, if your f, the function, represents the force, represents the variable force, obviously variable force acting on a particle along the curve, let's say AB, then the total work done is given by the line integral. Work done for the path AB, A to B, f dot dr. Okay, so obviously it is path dependent. Another case we can consider, if let's say v, a vector, represents velocity of a liquid, then what will this v dot dr represent? Is called the circulation of v round closed curve C. Okay, now look, two things are possible. One thing is when you are going from A to B, this is one way, right? Now when you are completing a path, if you are closing the path, you are going coming back, so you are making a closed loop. Then instead of a normal integration, we will write some circle here. Okay, so this is the third point. When the integration is carried on a closed curve, then instead of using this, we use this symbol, right? Now let's specifically talk about the work done thing. Now let's give you the concept of conservative force field. This is very important, question may come from this. Conservative field. As I told you previously also, let's say we have 2 points A and B, and it is we are evaluating the line integral for a vector function along this curve from A to B. Now if you consider different paths, in general the line integral will be different, but when the vector function acting here is conservative in nature, then the line integral will be independent of the path. It means whether you go along this path or along this path or along this path, the line integral value will be same. So what is the criteria for this being time independent, being path independent? That the function, vector function should be conservative. Now how to identify whether a function is conservative or not? If a vector function is conservative, then it can be written as the scalar of some gradient of some scalar function. Okay. So if you want to write the definition of conservative field, we can simply write a conservative vector field is a vector field that is the gradient of some scalar function. So the well-known example, you know, that if f is the conservative vector field, we know that it can be expressed as the gradient of some scalar function. Okay. So we give a minus sign, so that is case dependent, but in general we can just simply write, if you do not know, if you do not force, if you are writing in general, then it is that vector is equals to gradient of some scalar function. Okay, I hope this is done. Let us consider 2 points. One point is P, another point is Q. Now what will be the work done in taking and moving a point from point A P to point P, from point P to point Q? So work done by a conservative field let's say A in moving a particle from point P to Q will be, what will be the expression? You see, it will be integration from P to Q f dot dr, right? So as I told you, P to Q f dot dr, f can be written as grad of some scalar function if you consider that it is conservative. As I told you, we have already defined it as conservative field. So it can be written as the gradient of some scalar function, phi is some scalar function, dot dr. So what is this value? P to Q. This will become, you see, del phi by del r, okay, d phi by dr. So dr is cancelled, so d phi. So this is phi evaluated at Q minus phi evaluated at P. What does it mean? What does it mean? It means the value of phi at this final point Q and phi P is the value of that function phi at this point P. So it is only depending on the initial point and the final point. It is not depending on the intermediate points, hundreds and thousands of intermediate points. It means if I choose a path like this, then also this integral value will be same, because it is only depending on the initial and final point. If I choose another path like this, it will also not change this value of this integration. Whatever path you choose, it will not change the value of this integration, because for this conservative field we have we have proved that it is only depending on the initial point and the final point. So that is why for a conservative field the line integral is independent of path, independent of path chosen to move from one point, chosen to move from the initial to final point. Now one thing you see, as I told you, for a conservative field, for any vector, let's say A, this is conservative in nature, conservative field. What is the definition of conservative field? How to check? If I give you a vector function, how to check whether it is conservative? So first of all, it can be written as the gradient of some scalar function. Now if you just take the curl of this vector function, what do you get? You get curl of grad phi. And what is the meaning of this? Curl of gradient. Curl of gradient is 0. Curl of gradient of a scalar function is 0, and that is why the best way to check whether any given vector field or vector function is conservative or not, to take the cross product, to take the curl. If the curl come out to be 0, then that vector will be conservative in nature, otherwise not. One example on this regard, this came in CSIR-NET June 2014. So I hope you understood the basic concept of line integral. Let's consider some problem now. If A, this is the vector given to you, C is the circle of unit radius, that is okay, in the plane defined by z equals to 1 with the center on the z axis, then the value of this integral, closed integral C A dot dl. Why this closed sign? Because you are considering a circle. Circle is a closed structure, right? That is why this closed integral is shown, and C is the name of the curve. Can you solve this problem? If I consider the situation, let's say this is x axis, this is y axis, and this is z axis. C is the circle of unit radius in the plane defined by z equals to 1. So this is z is equals to 0, and let's say this is z equals to 1. Your circle is situated at z equals to 1 and with the center on the z axis. Means the circle is like this. Okay, it has unit radius, this is 1 unit, and this curve is termed to be C. So you have to find out this closed integration E dot d. Okay, another thing I think I forgot to mention, that line integral of a conservative. Okay, look, if this vector A is conservative, then the line integral over some closed curve will always be 0. Okay, this will happen because of this vector field A is conservative in nature. Okay, so let's evaluate this. So first of all, let's check whether this function is conservative or not. So to do that, we have to calculate curl of A. What is curl of A? Can you calculate curl of A? Curl of A we can write it as I cap, j cap, k cap, del del x, del del y, del del z. A vector yz, zx and xy. So if you calculate this curl, what do you get? Okay, this is, we are getting x minus x plus j cap y minus y, k cap z minus z. So this is coming out to be 0. As since the curl is 0, we can say that A is a conservative field. A is a conservative field, and hence we can say that the closed line integral A dot dl or dr will also be 0. So option D is the correct option for this question. Simple thing, no issue. I am now giving you another problem, and by that problem you will be able to understand this line integral pretty well. Okay, so the problem is like this, that you have to evaluate. Let me just write the problem, then we will discuss the solution. Simple problem, but essential to understand the line integral efficiently. Okay, so the problem is like this. Evaluate this line integral f dot dr, where your f is given to be x square I cap plus xy j cap, and C is the boundary of the square in the plane z equals to 0 and bounded by the lines. What are the lines? X is equals to 0, y is equals to 0, x equals to a, and y is equals to a. So this one you need to evaluate. How will you do that? So this is first of all a square, right? Square, we are considering this is the square, and we do not know. Okay, let's say this is the origin, this point is the origin, and this is x-axis. Let's say this is x-axis and this is your y-axis. For our convenience, we have denoted the x-axis and y-axis, and as this is the plane z equals to 0, z equals to 0 means xy plane. On xy plane at each and every point z equals to 0, so we have, that is why we have taken xy plane, right? Bounded by the curve x equals to 0. Which one is the x equals to 0? This one is x equals to 0, this line, right? This line is nothing but x equals to 0. On each and every point of this line, x will be equals to 0. Y is equals to 0. Where y equals to 0? Obviously this is your y is equals to 0. At this point, each and every point, whatever point you consider, y will be equals to 0. X is equals to a. X equals to a will be this. If I consider, let's say OA BC, this is the square. If I consider that this side length is a, then obviously this line is x is equals to a, and this BC, this line is y equals to a, because at each and every point here you will get y equals to a. So these are the 4 lines along which you have to find out the line integral. So you see, it is taken in the anti-clockwise direction. Okay, always take the closed curve C to be in the anti-clockwise direction. So you are evaluating the line integral along this path OA, AB, BC, CO, right? So line integral along the closed curve f dot dr, if I just simply write it, how will you write it? F dot dr, first of all along the path OA, then we'll add this to the line integral along the path AB, then we will add the line integral along the path BC and then CO. So these 4 line integral you have to calculate to get the line integral of f dot dr along this closed path. Here C is the whole square path, okay, the perimeter. Now what you require? We require f dot dr. F is already given, this one. We require dr. So what will be dr here? So it is effectively 2-dimensional case, right? It is varying in the xy plane. So as I already told you, it will be dx I cap plus dy j cap. So if this is dr, then what will be the value of f dot dr? F dot dr will be, that take the dot product, x square dx plus xy dy. Now let us calculate the line integral along each path. First of all, we will consider the line integral on OA, right? Or simply you just write OA. So on the path OA, what we can write? On OA, what we have? We have y equals to 0. So if y equals to 0, then what we have? Only x square dx you have. F dot dr is x square dx, because the second term is 0, and that is why the integral on OA f dot dr, it is nothing but integration of x square dx. Here limit of x you have to put. What is the limit of x? 0 to a. 0 to a. So this is x cube by 3. So this is a cube by 3. Okay. Let's go for AB. For AB, what we have? X equals to a, right? X equals to a. So what will be the value of f dot dr? A square, and here x is not changing, so dx is equals to 0, right? So the first term is vanishing and x equals to a, so this is nothing but ay dy. Here dx is also equals to 0, and here dy is 0. So along the path AB, what is your f dot dr? It is nothing but a times y to dy. Y is varying from 0 to a, right? So this is y square by 2. So a square by 2. This is also a cube by 2. So I think you can easily calculate now the line integral from B to C and from C to A. So let's calculate for B to C. So along the path BC, what we have? Along path BC, we have y equals to a, and you see the value of y is constant. So y equals to a and dy is equals to 0. So what is f dot dr? Only the first term will remain, x square dx. Okay. and hence the line integral f dot dr along BC, right? Yes, BC, it becomes integration x square dx, and you see x is varying from a to 0, right? Here at point B x equals to a, at point C x equals to 0. So that is why the limit is a to 0, and this will be x cube by 3, limit a to 0. So a minus sign will come, minus a cube by 3. BC is done. Let's go for CO. On this line, what we have, x equals to 0, dx is equals to 0, x equals to 0, dx is also equals to 0, and f dot dr equals to x equals to 0 means in both the term x is there, so this term will basically 0, and obviously CO f dot dr is also 0, right? Now if you want to get this whole line integral along the whole path, closed path, entire path, f dot dr, then you have to add each of these integrals. So out of these 4 integrals, the last integral is 0, and the first two integrals are a cube by 3 and a cube by 2. Just add them up. So the first integral is a cube by 2, second integral, sorry, a cube by 3, second integral a cube by 2, third integral minus a cube by 3, fourth integral 0. So a cube by 3 is getting cancelled, so only a cube by 2 remaining. So this is the answer. So I hope you have understood this problem. It's a very interesting problem. Once you understand this problem, then I think your concept on line integral is also clear. Let's move on to this problem. This problem is a simple problem. Look at this problem. The line integral a to b f dot dl, where f is given by this along the semicircular path as shown in the figure. Here this is a semicircular path, and as you can see, the line integral is to be evaluated from a to b, and you can see the direction. It is in the clockwise direction. If it were anti-clockwise, then b to a. Okay. So how can you solve this particular problem? Look, x by root over x square plus y square plus y by root over x square plus y square. Now if you look at this geometry, Cartesian, instead of using Cartesian coordinate, if you use polar coordinate, then that will be suitable for us. Okay, these expressions can be reduced, and from this minus 1 0 to plus 1 0, we can say that this radius of this half circle is nothing but 1. Okay, this r is equals to 1. So we are dealing this problem in Cartesian, let's say polar coordinate. In polar coordinate, what do you say? What do you take? We take, first of all, let's write what we have to do. We have to do a to b f dot dr. So this is nothing but point A is minus 1 0, so we have to go to plus 1 0 along the vector function along the curve of the semicircle. So x dx by root over x square plus y square plus y dy by root over x square plus y square. This one you have to evaluate, right? Now we are using polar coordinate, plane polar actually. Look, when you are considering in 2 dimension, it is plane polar. When you are considering the 3 dimension, that is spherical polar. So using plane polar coordinates, we can write x is equals to r cos theta, but as you can see here r equals to 1, so we are simply writing it as cos theta. So dx is equals to how much? We need dx here, as you can see. Dx will be cos theta, so minus sin theta d theta. What you require? You require x dx. So let's calculate x dx. X dx is nothing but x equals to cos theta, so minus cos theta sin theta d theta. On the other hand, we have y equals to r sin theta. R is equals to 1, so it becomes sin theta, and that is why dy is nothing but cos theta d theta, and y dy becomes y is equals to sin theta cos theta d theta. If x is equals to cos theta, y is equals to sin theta, then we can write x square plus y square is nothing but cos square theta plus sin square theta, that is 1. Okay, so obviously root over x square plus y square, that is also equals to 1, and therefore the integral a to b f dot dl becomes, you see, what will be the limit from x y coordinate to r theta coordinate we have converted. So let's calculate it. Let's calculate this thing. So previously, what was the limit of x? The limit of x was minus 1 to plus 1. Y is 0. The final initial y is 0. R0. Sorry. What is the value of theta? For if you consider this one, x is equals to minus 1. So for what value of theta? Cos theta is minus 1, that is pi. And for 1 it is 0. So it is nothing but pi to 0. X dx is minus cos theta sin theta d theta plus y dy is sin theta cos theta, d theta we are taking common. So we have to integrate this from pi to 0, and whatever be the integration result, that will be the answer. But you see, these two terms are cancelling, so this is 0. So the whole integral becomes 0. Option B is evaluated to be the correct answer. Okay. So I think this is enough for line integral. Next we are going to move to surface integral. Surface integral is also very interesting thing and easy as compared to the line integral. Okay. So let's talk about surface integration of vectors. Surface integration of vectors. So obviously previously we are defining the line integral over some curve or line. For surface integration we will consider a surface. Obviously the surface integral will be defined over a surface. So initially previously what was there? We had a curve, a vector function. Here also a surface will be there, and for usual region there will be a vector function. So you are evaluating the surface integral of this vector on this surface. Okay, this is the main idea. So let's write. Now surface can be of two types, right? You have seen different kinds of surface. Only different types of surfaces include open surface and closed surface. Closed and open surface, you can see. Closed surface is that surface which contains some volume, like a sphere. An open surface is that surface which does not contain any volume, only area. Like if you consider a rectangular plate, very thin rectangular plate, that is only containing the area, not containing any volume. So that is the open surface. So the integration of a vector on an open or closed surface is known as surface integration of vectors. To make you understand it more clearly, you can see this figure. This is a sphere. It contains some volume, so that is why it is a closed surface. This is simply a plate, does not contain any volume, that is why this is an open surface. Okay, thin plate. Understood the definition? Now let's say an infinitesimal area we are considering here, that is ds. The way we define line integral, the surface integral is defined in a very similar way. For line integral we took the tangent. For surface integral we have to consider the direction of the area vector n cap. So let A be a vector function and S be the given surface. Then we define the surface integral of a vector function A over the surface S is defined as the integral component of A along the normal to the surface. Okay, mathematically if I consider the component of A along the normal, so obviously as I told you already, it is a dot product of that vector and the unit vector along that normal direction. So A dot n cap. What is n cap? N cap is the unit vector on this infinitesimal area ds. ds is some infinitesimal area. So n cap is nothing but the unit vector normal to ds. Okay. So what is the component of this surface integral? Ultimately how do you define surface integral of A if you consider over this whole surface? Previously we consider only ds, no? So if you want to consider over the whole surface S, then we have to take the sum over all such infinitesimal area. Now this is a continuous thing, so it can be converted into a surface integral, into an integration. So A dot n cap ds. Right, now two integrations, because if you, there are two dimensions involved, that is why two integrations are there. If you go to volume integral, there will be three integrations. On this regard, let's talk about the volume integral. The volume integral is pretty simple because volume is a scalar quantity, so it is very easier to handle than the other two cases. Volume integral of vectors. volume integration of vectors. So volume integral of a vector field A within the volume V, what's happening, is given as, we simply write it, triple integration, volume integration is carried out over the volume V, vector A dV. You can imagine that this is the vector, this is the volume, and dV is the infinitesimal volume. So you can imagine it in this way. The way you imagined ds, some infinitesimal area, this is your infinitesimal volume dV, and the whole volume is V, and the volume integral is A dV. Now there are two very important theorems, divergence theorem and Stokes theorem, relating to this open surfaces and closed surfaces. And this divergence and Stokes theorem will help you to convert from line integral to surface integral to volume integral in this way. So let's talk about those two theorems. Those theorems are very important, vector related theorems. Most of the question from vectors previously came from this particular topic. Two theorems. One is the divergence theorem, another one is the Stokes theorem. You have to remember the mathematical expression for these two theorems. क्या हो रहा है? Okay, first of all, let's talk about the applicability. Divergence theorem is applicable only for closed surface. This is applicable only for closed surfaces. What does it mean? You can apply it to spheres, let's say cylinder. You cannot apply it to some thin disk or plate. On the other hand, Stokes theorem, it is applicable only for open surface. Open surfaces like this. This is an open surface, it doesn't have any volume. Open surface is bounded by some curve. You see, this is the curve which is binding the open surface. So the Stokes theorem is applicable for open surface. Now what is the purpose of introducing divergence theorem? Basically this theorem, what it does? It basically converts surface integral into volume integral. And the vice versa is also possible, means from volume integral you can come back to surface integral. So you can simply write surface integral to volume integral and vice versa. And what about this Stokes theorem? This theorem, it basically converts surface integral into line integral. Surface integral is common in both. surface integral into line integral, and vice versa. Means from line integral you can come back to surface integral. Let's talk about that basic statement in these two theorems. Then we'll go for the mathematical form. So what is divergence theorem? Divergence theorem, it obviously contains some volume. So V will come here into picture. So if V is the volume will be bounded by surface. Okay, now for a closed surface, and for open surface the area will be bounded by some curve, a line. So if V is the volume bounded by a closed surface, let's say S, and A is the vector function. A is the vector function of position, function of R, with continuous derivatives. Then there is no discontinuity in the derivatives. You take different derivatives, then there will be no discontinuity. Then we write the mathematical form of divergence theorem as, look, when you consider a closed surface, you see the surface of this sphere, it is closed, not open. So that is why we give this symbol of closed. We have already introduced it. Closed integral over the surface S A dot ds. So this is your surface integral. So surface integral we can convert it into volume integral. Okay, and this surface integral has all the form, other form. Ds is what? Ds is nothing but, if you consider the vector ds, it is nothing but the magnitude of ds and the direction n cap. So that is why sometimes we write a dot n cap ds. This is equals to the volume integral. Volume integral here will be v, and it will be divergence of a dd. So it basically converts surface integral into a volume integral. On the other hand, if you consider this open surface S, so how many surfaces it will have? An open surface will have two ends, like above, below. So if S is an open, two-sided, one above, another below, two-sided surface. Look, here volume was bounded by closed surface. Now surface will be bounded by some line. Surface bounded by a closed, you see this line is closed, non-intersecting curve. Let's call this curve to be C. So surface is S and the curve which is bounding that is C. So you can consider this is S and the curve bounding it is denoted by C. If S is an open two-sided surface bounded by a closed non-intersecting curve C, and A is vector function of position with continuous derivatives. So you can see the languages are very similar. Then mathematical form we can write. What do you have to do? Surface integral into line integral, or line integral into surface integral. So here the mathematical form is Here also closed. The curve name is C. A dot dr, this is line integral. It will convert into surface integral. Surface integral, two integration sign will be there. And here you are not giving the close because surface is not closed here. For a closed surface, the surface is closed, but for an open surface, the surface is not closed. So that is why no closed symbol is given here. Curl of A dot n cap ds, or you can simply write it in this way, curl of A dot vector ds. And as you can see, C is traversed in the anti-clockwise direction. This is the positive direction, where C is traversed in the counterclockwise or in the positive direction, in the positive or counterclockwise direction. So I think you have now pretty much understood these two theorems, and there is a high chance that you will get some question from these two theorems. Let's try some problem. The first problem is this on your screen. If a vector function A is equals to xy x cap plus x square y cap, then what is the value of this line integral A dot dl over the path shown? So here on this path you can see the x value is varying from 1 by root 3 to 2 by root 3, and the corresponding y values are varying from 1 to 3. So A dot dl you have to find out. What will be our first job? Our first job will be to check whether this is conservative or not. If it is conservative, we can simply say it is 0. So let's check whether it is conservative or not. Okay. So to check conservative, whether it is conservative or not, we have to take the curl. So let's say x cap, y cap, z cap, del del x, del del y, del del z. What are the x, y, z components? X component is xy, y component is x square, and z component is 0. So what you get? X cap, this is 0, minus y cap, this is also 0, plus z cap 2x minus x. So this is nothing but x z cap. So curl of A is not 0, so we cannot say that A is conservative. So we have to calculate. We have to calculate A dot dl. A dot dl. We can use the Stokes theorem. Okay. So we can write the line integral in terms of the surface integral by considering curl of A dot ds. Okay, over this surface. This is the surface. What about ds? Ds, you see, this is on the xy plane. So ds is nothing but this area. What is that? Along this side, this is dx, this is dy, and if you take in a counterclockwise sense, what will be the direction? It will be k cap, right? If you rotate it along this, it is coming out this. So ds is nothing but dx dy. What will be the direction? Z cap. Because when you consider the direction of area, it is perpendicular to that. So if you are considering the element in the xy plane, obviously the perpendicular direction will be z cap direction. That is why we have written dx dy z cap. So this becomes integration curl of A dot ds. So here x dx dy. What are the limits of x and y? X goes from 1 by root 3 to 2 by root 3, y goes from 1 to 3. So let's directly put that x going from 1 by root 3 to 2 by root 3. On the other hand, y going from 1 to 3. So dy we can calculate. Dy is y, 3 minus 1 is 2. Okay. And x ds is x square by 2. So 1 by 2 we are taking common. So x square by 2. So 1 by 2 we have taken outside. X square means square of this thing. So 4 by 3 minus square of this thing 1 by 3, and from this integral of dy we are getting 3 minus 1 is 2. So this is nothing but 1. So this value of this integral over this path on is 1. Option B is coming out to be correct. Clear? I am giving you a similar problem as homework. You can try it at home. The line integral, similar problem, very similar. The line integral A dot dl over a vector field, A value is given to you, where r square is equals to x square plus y square is taken around a square of the side of unit length centered at x naught y naught with x naught greater than half and y naught greater than half. If the value of the integral is L, then what will be the correct option among this? Right. Line integral you have to find out. Basically you have to find out A dot dr or dl, whatever you write, over this curve C. Curve C is this. As you can see, it is in the clockwise direction anyways. So on this curve we have to find out this line integral, and as you can see this is closed curve, right? So your what will be your first check? Your first check will be whether this field is conservative or not. If it is conservative, you can directly say it is 0 and independent or anything. So for this you will see that the curl will come out to be 0. So L will be equals to 0 and it will be independent of x naught y naught. So option 3 will be correct answer. Take this as homework. Just you will evaluate the curl of this function, curl of A, and this will give you the result 0. So option C, option 3 will come out to be the correct option. Okay, now let's move on to this problem. This is the last problem and we'll wrap up the session here. The value of f dot dr, where f is equals to this, you can see f is nothing but y by x square plus y square I cap minus x by x square plus y square j cap. So we have already done this similar kind of problem before also, today itself. Traversed counterclockwise. So by looking at this x square plus y square and circle, it will be better idea. It will be a better idea to use plane polar coordinate, right? Okay. So when we do not know in which dimension we need to carry, we can generally take it 3 dimension. Okay. So dr, what will be dr? Dx x cap or I cap plus dy j cap plus dz k cap. And as you can see, when we will take the dot product of f and dr, obviously this k cap will vanish. So it is finally coming out in 2 dimension. So close integration f dot dr you have to find out along this circle path, x square plus y square equals to 1, traversing counter clockwise. So it is a circle on the xy plane with radius 1. So first of all, f dot dr, if you calculate, what will be its value? It is nothing but, you see, I cap and I cap, y dx is coming, y dx divided by x square plus y square, and here minus x dy divided by x square plus y square. This is coming, and x square plus y square is given to be 1. So it is nothing but y dx minus x dy. This one ultimately you have to find out. Why you could write? Because x square plus y square equals to 1. So it will be a better idea if you go with the plane polar coordinate. So we can put x is equals to, and r is equals to 1. So r cos theta. So we are not writing r equals to 1, you know, x equals to cos theta, y equals to r sin theta, means y equals to sin theta. So it is kind of similar problem which we have done earlier. Dx will be minus sin theta d theta, and dy will be cos theta d theta, right? And hence your f dot dr will become, again you can use this technique to change the value of these limits. So if you want to change the value of this limit from x, let's say x to theta, okay, then you can do that. Or you can simply write, if you do not do this, you can simply you can write that the value will be 0 to 2 pi. Theta is varying from 0 to 2 pi. Ultimately you are representing theta, na? In plane polar coordinate the value of theta varies from 0 to 2 pi, right? So 0 to 2 pi, y dx, y is sin theta, dx is minus sin theta d theta, minus cos theta d theta, and we know the range of theta to be 0 to 2 pi. So minus sin square theta, minus is taken outside, 0 to 2 pi sin square theta, and plus cos square theta. You can write it in this way, d theta. This is 1. So minus theta varying from 0 to 2 pi. So minus 2 pi it comes. It is matching with option 4. Option 4 is the correct option for this question. Okay, so in this lecture we have covered the line integral, surface integral and volume integral in detail with some numerical, and we also discussed some vector related theorem, the most important, divergence theorem and Stokes theorem. And I hope this lecture will be very beneficial for all of you in various examination like CSIR-NET, GATE, JEST, TIFR, BARC. Everywhere you go, this thing will be equally helpful. Okay. So we have covered this much, and from the next class we will start quantum mechanics. Okay. So you can consider it in this way, that the first 3 days of the week, Monday, Tuesday, Wednesday, will be going for MMP, mathematical methods of physics, and in the next 3 days maybe quantum mechanics, means Thursday, Friday, Saturday, and every day we'll try to take the class at 8 AM. So try to attend the class live. These classes may not be live for a long time, so it is asked to attend the classes live. That will be useful for you if you attend the classes live, and all these classes will be uploaded in the app also. You can also get all the lectures and the PDFs of this class notes in the app itself. You can get the app by scanning this QR code, and by also visiting this website you can get the app, or you can simply download this app from the Play Store. And you can join the Telegram channel by using this Telegram channel ID, and you can also join the WhatsApp group. The WhatsApp group is given in the description. So thank you very much guys for watching this session. If you are new to this channel, please subscribe the channel and don't forget to press the bell icon.